All right, so if I remember correctly, you guys just started talking about the antiderivative going backwards. Does that sound about right? Okay. And most recently, you guys were investigating an integral, meaning the area under a curve. Is that right? You guys did like left endpoint, right endpoint, midpoint, trapezoid, okay? And we still have a few tables to go over, right? Is that correct?
Yes.
Okay. Are we on part B? Part A?
Yes.
I forget. B? Okay, so let's just kind of take a look at what this is asking. Approximate, meaning the little squiggles, okay? The integral, meaning area under the curve of this f of x graph, but we don't have the graph of this function, okay? We have a table in this case. We have certain data points to use. We only want the area under the curve from 0 to 15 on the x-axis. So we might not use all of this information. We just want to use what's necessary for this particular question. We're going to use a left endpoint sum. Okay, we're going to add up all those different rectangles, and we specifically want 4 rectangles. Okay, so if you take a look at the table, it's the same for all of them. We're only going to go from 0 to 15. So this 20 and 25, not really relevant for this problem if you want to cross it out. So you got to ask yourself, how can you go from 0 to 15 in this table and divide it into 4 rectangles? Can you tell me where one rectangle would begin and end, where another rectangle would begin and end? Based off of this table, the numbers that were given to us. Sometimes I like to draw like little rectangles above as a visual. Can you describe where they might be? What do you think, Braden?
7 to 4, 4 to 7.
Okay.
7 to 12, and 12 to 15.
There we go. Okay, so we went from 0 to 15 using 4 rectangles. Now the rectangles might not always be the same length. Okay, we don't have the luxury of making them all the same length like we did in the graphing examples because we only have a table. We only have certain numbers to use. So there's our 4 rectangles. So let's go ahead. The integral, aka area, under the f of x graph is roughly, okay, so we'll get to the approximations here. So our first rectangle goes from 0 to 4 on the x-axis, so that you can think about it as the base of the rectangle. So that's 4 units. But you know, to find the area of a rectangle, you need base times height or length times width, whatever words or phrasing you use. So if we want a left endpoint, if 4 is the base unit, where's the height going to come from? We need to make sure the height is the left-handed side of the curve. What do you think? Yeah? 15. The 15, right? Okay, height, aka y value, like how tall are the y values that the graph goes up to. So from 0 to 4 is the base numbers you can use, but 15 and 6 are the heights. And the one on the left-hand side is the 15. So we need 4 times 15. So there's the area of our first rectangle. Let's go ahead and now repeat the process, but for the other 3 rectangles that we listed. So the next rectangle goes from 4 to 7. That base length on the x-axis would be 3. 4 to 7 is 3 units. But now we got to find the height on the left-hand side of that rectangle. It'd be 6, yep. Notice how that's the left-hand side of this rectangle that I have here over the 4. So we need 3 times 6. Okay, we're going to repeat the process. The next rectangle goes from 7 to 12. That's a base length of 5. The left height is -5. That just means you're below the x-axis. And our last rectangle, we have 12 to 15, so that's a base of 3. And the left endpoint is -10. All right, so go ahead and calculate those individual areas, add them up. Let's get an approximation to the area under the curve. Any takers? Good, Stevie?
23.
23, sounds good. How'd you do? Good? Okay. I wanted to highlight one thing just because this one's a little bit more difficult. If you already did part A, the midpoint, and we want to do 3 subintervals, I think those are the ones you used. I do have some students sometimes that kind of question how we can use a midpoint, because notice how if we go from 0 to 7, we know the middle of that interval is 3.5, right? But we don't have the luxury of knowing a 3.5 value. That's why we have to use the 4. Was that covered before? Good. Really good. Okay, perfect. Do you guys think you can try part C? Okay, be careful of what the integral is telling you to use. What are your bounds? Where are you beginning and ending? Notice how we go from 4 to 20. So you're not going to use the whole table in this case. All right, and we want a right-handed sum, again with 4 subintervals. What'd you guys got? Good, Braden?
Negative 31.
Negative 31. Sound good? Do we need to go over that one? Speak now, forever hold your peace. We do. All right. Let's try the next one. Approximate the integral, aka area under the curve, 0 to 25. So we're going to use the whole table, or at least we should. We might not use every value in the table, but we're not going to cross out to ignore any values at least. This time we want a trapezoidal sum with 3 subintervals. So let's go ahead and section off this table. How can you go from 0 to 25 and section it off into 3 pieces? 3 trapezoids. Good. Joseph, sorry.
0 to 7.
Uh-huh.
7 to 15.
Yep.
And 15 to 25.
15 to 25. Awesome. All right, so this one we have to be a little careful about because all the other ones were rectangles. This time we're going to do a trapezoid. Do you remember the formula for the area of a trapezoid? A little difficult, yeah.
1.5 times the height times B1 plus B2.
B1 plus B2, okay.
That's your limit. Thank you.
Sounds good. All right, so let's take a look at our first trapezoid. We need a 1/2. We got to figure out what the height is. We've got to be careful with the word height and what the bases are. Okay, so when you think about a typical trapezoid, at least when you were in geometry, they all looked like that, where this was the height and this is base 1, base 2, however you want to label it. How we draw the trapezoids, if you remember from the other day, they were kind of rotated like that, right? Because these were points on a curve that you were connecting. Okay, so notice how it's a height. We label it as h, but the h is actually on the x-axis because you rotated it. So you can't really think about the h as a height, meaning vertically, because if we rotate it, now it's going to be horizontally. So the h is the height or the distance on the x-axis. This one we're going from 0 to 7 on that x-axis. So that distance would be 7. Notice how the bases switch as well. The bases are now y values. You're going up to a particular height on the curve. So what might we label as base 1 and base 2 from the table? -15 and -5. Yep, those are the heights at the two endpoints of your trapezoid. And we got to add them together. So 15 plus -5, or 15 minus 5, same thing. So there's the area of your first trapezoid. We're going to repeat the process for the other two. All right, so we need 1/2 times the height, but the height's on the x-axis. We're going from 7 to 15. So that's a distance of 8. And then we need the bases, meaning the heights of the endpoints. So that would be -5 again. And we got to add -2. Our last trapezoid, we go from 15 to 25. So that's a height, in quotations, a height of 10. And then the bases of the endpoints, we have -2 plus 20. Go ahead and see what you get. How does 97 sound? Good? Perfect. All right. That's the end of this section with midpoints, right endpoints, left endpoints, trapezoids. Okay. We doing okay so far? Are there any homework problems you guys want to go over before we start the next section? No? Do we think that section's kind of easy? It's just rectangles and trapezoids, okay, geometry shapes that we're used to. All right, so next section on page 351. Up to this point, you've been doing integral approximations, okay, using little squiggly lines. We've been trying to see what the area is close to. We're actually going to use calculus now, okay, derivatives, antiderivatives, to help us find the integral, aka area value, exactly. Okay, so no more squiggly signs. We're actually going to use equal signs. How we go about this, it's important because it has a particular name to it. Okay, the fundamental, the important, the foundational theorem of calculus. Part 1, we're going to have another one later on. But this is going to give us a way to find an integral value exactly. Okay, so we're going to write it down, but then we're going to make sure we understand it as we go through some examples. All right, so a few things we got to make sure first. If f of x is continuous and differentiable, there's that big word from earlier this year, on an interval. Let's go ahead and refresh our vocabulary. What does continuous mean? No holes, no jumps, no asymptotes. You can draw it without lifting up your pencil. Do we remember the 3-part definition to continuity? Like the mathematical definition? There were 3 things you had to check. I believe we were in the Audion when we did this, or maybe it was 8th period we did this. My bridge example. Yeah? There we go. The point, the limit, and they match. All right, so the point exists, meaning the bridge exists. The limit exists, meaning the road, right? And the bridge and the road have to meet up for you to go across the river. Okay? Continuous. So no holes, no jumps, no asymptotes. You can draw without lifting up your pencil, and you have that 3-part definition. What about differentiable? There's a vocab word for you. Yeah?
The derivative is
The derivative exists. Okay, so you can pick a point, any point on this f of x graph, and you can draw a tangent line. Okay, the derivative, aka tangent line, aka slope, exists. What are some things graphically that signify a slope not existing? You cannot plot a point and draw a tangent line. Yeah.
When it comes to a peak.
A peak, okay, a sharp point or cusp, something like that. Yeah.
straight up and down.
A vertical tangent, okay, because the slope of a vertical line is undefined, yeah.
An endpoint.
Or an endpoint. Good, good, good. Also holes, jumps, and asymptotes, because those don't match up exactly on graphs. Perfect. Okay, so it has to be continuous, and a derivative must exist. Okay, so if both of those are happening on an interval, then the integral, the little S shape, from A to B, okay, your beginning value and your ending value of f of x dx is equal to capital F of B minus capital F of A. And we're specifically going to label this capital F is the antiderivative. All right, so might go over your head a little bit, but we're going to kind of decipher it so that it makes sense. Let's go ahead and just take a look at the first example and relate it back to this fundamental theorem of calculus. We have this easy function. It's a line. You did lines back in Algebra 1. Okay, we're eventually going to amp it up with different types of functions, but for now we have a line. Here's the equation. They gave it to us. Calculate each of the following integrals based off the fundamental theorem of calculus. Okay, so we're going to try to figure this out. The area under the curve, okay, the integral is exactly, notice how I used equal signs, this antiderivative idea. So if we take a look at this integral, we want to find the area under the curve from -2 to 1. Let's just go ahead and shade that in here so we can visually see what we're trying to find. So if you started at -2 on the x-axis and went up to the curve, and then you went to 1 on the x-axis going up to the curve, we're trying to find all of this area. We're not going to use left endpoints, right endpoints, midpoints, nothing like that, because we want to try to find it exactly. Okay. Now if you take a look at that shaded region in there, is that a geometric shape that we are already familiar with? What does that look like to you? It's a trapezoid, exactly. Okay, so we could probably use the trapezoid formula to find the area exactly. We're not going to use calculus for this, right? We're just going to use some geometry properties. But I'm going to show you how using calculus can get you to the same result. Okay? It's just when you don't have a nice geometric shape to identify is when we have to use calculus. What's our area formula for a trapezoid again? 1/2 height, base 1 plus base 2. Okay, so looking at this geometric shape that we kind of shaded in, the height goes from -2 to 1, which would be 3 units. And then we need the base values. So from the left-hand side, it has a height of 7. That could be our base 1. On the right-hand side, it has a height of 1. So that'll be our base 2. So 1/2 times 3 times 8 looks like we get 12. Okay, so we know the area is exactly 12 just by using some geometric formula, but let's see if we can get the same thing using calculus. Okay, so let's check this out. The exact area under the curve is defined as finding an antiderivative, okay, working backwards, and then somehow using B and A, in other words, the upper and lower bound, to find that actual area. let's go ahead and find the antiderivative first. Okay, we're going to work backwards. I think you guys have done this a little bit so far. If you have a negative 2x right now, what did you have before that? Like before you took a derivative and got negative 2x. Yeah?
Negative x squared.
Negative x squared, good. Remember, you got to add 1 to the power and divide by that new power. Looks good. All right, if you work backwards from a 3, what did you have before? 3x. Is there something else you need? Plus c. Good, good, good. Plus c. I will tell you right now, okay? If you forget the plus c, you will lose a point. On my tests, on the AP tests, okay, you lose a point. Sometimes you might not need the plus c, and we're going to get to that, okay? But forever and always, please try to remember the plus c, okay? Are we okay with finding an antiderivative? Okay. So we did this part. We found what the antiderivative was, but notice how we got to evaluate the antiderivative at b, which represents the upper bound, and we need to subtract evaluating the antiderivative at a, which is that lower bound. So what I want you to try to think about, or just remember, is top minus bottom. At least this is how I remember it. After you find the antiderivative, we're going to plug in the top bound from the integral, and we're going to subtract, plugging in the bottom bound, or the bottom number. All right, so we're going to plug in 1 into all of these x's and see what we get. 1 squared is 1, and then we have the negative out front. If we plug in 1 for the next x, we'll have plus 3, and then we have plus c. So this is what we get. This is representing the f of b part. We found the antiderivative, and we plugged in the top bound. Now we're going to subtract what we get when we plug in the bottom bound. So we're going to plug in negative 2. Negative 2 squared is 4, but we have that negative out front. So it's going to change it to negative 4. If we plug in negative 2 for the next x, we have negative 6, and then we simply have that plus c. So now it's just evaluating using some algebra or arithmetic. We have negative 1 plus 3 plus c, but since we're subtracting, you have to distribute that minus sign through. So we'd have plus 4 plus 6 and then minus c. Do you notice anything that's going to happen? C's cancel, and we get 12. There we go. Okay, so using an antiderivative, we're going to do top minus bottom, plug in the top bound minus the bottom bound, and we'll get the exact area under the curve. Now we know it's exact because we were able to check it using the trapezoid formula, but if we have a really crazy shape, trapezoid might not always work. Rectangles might not always work, but calculus will always work. Okay, here's the other thing. Braden said that the c's disappear. Okay, I want you to make note of this. When you know the bounds, okay, meaning the top bound and the bottom bound on the integral, when you know the bounds, you don't need plus c on your antiderivative. Because if you know the bounds, the c's will always cancel. So don't write it if you don't have to. Yes?
If we don't have to, we write it.
That's fine. Okay?
Be safe.
To be safe, always write it. Okay? But as a little shortcut, if you know the bounds, you don't need to write the plus c. If that 1 and that negative 2 were not there, you would have to need the c. Okay? But the fact that they are there means that they would cancel out in the evaluation process. So you don't have to write it. Okay? But always safe than sorry. Okay? Let's go ahead and try the next one. We still have the same line. Okay? This time our bounds are from 2 to 5. So visually, let's go ahead and shade in that area. is that an easy geometric shape that we can find the area for? It's another trapezoid, right? Okay, so let's try this one. Our base is 3 units long. Or sorry, our height, I guess, is 3 units long. Base 1 is a -1 height, and base 2 is a -7 height. So 1/2 times 3 times -8. We have -12. Okay, let's see if we can get the same thing using calculus. Okay, because what if we didn't have the graph? We could simply have the integral, find the antiderivative, and do top minus bottom, and we get the same answer, hopefully. Okay, but at least the graph is a visual for us right now because we're still learning. If we do the antiderivative, we're going to have the same thing as before because it's the same equation. -x squared plus 3x. We don't need the plus c, though, if you don't want to write it, because we know what the bounds are. All right, let's go ahead and plug in the top bound. If we plug in 5, we'll have -25 plus 15. And we have to subtract what we get when we plug in the bottom bound. We have -4 and then a +6. So distribute in that minus sign, it'll change the last 2 signs. We still get -12. Checks out. We doing okay? All right. One little thing before we turn the page, just a little like mathematic notation that I do, okay, that's mostly common on the AP test. Whenever you know the bounds, okay, you don't need to write the plus c, but what you might sometimes see in a textbook or on a worksheet is this bracket at the end, and they will rewrite the bounds on the top and bottom of that bracket. What that bracket means is just that you are going to plug in 5 and 2. You're going to evaluate this antiderivative with those numbers. So you don't need the plus c, but you will see on my homeworks that we post online and in any textbook that you might reference, they'll have a bracket here with the bounds. Okay, so just something else you might want to write down to help you remember what numbers you're plugging in. Okay, let's go ahead and try the next one. Same equation, all right? This time we have different bounds. We're going from -1 to 4. So let's visually find that on the graph. Shade in the area to the x-axis. We want to find all of that blue area. Are those nice geometric shapes that we can use to our advantage? Those are triangles, right? Do you remember the formula for a triangle? 1/2 base times height. Okay, so this first triangle, the base is 1, 2, 3 units, and the height is 5 based off the graph. But now we need to add the area from the other triangle because we're trying to find all of this area. So the next triangle, the base is also 3 units, but the height is -5, okay, because it's below the x-axis. So what's going to happen when you add all those together? We get 0, okay? What's happening here is this first triangle, notice how its area is above the x-axis, whereas the other triangle has area below the x-axis. You can think about it as a negative area. If it's 0, that means you kind of have the same amount of area above and below. They're canceling each other out. Okay, so even though you can visually see area, the overall area is 0 because they cancel each other out. Let's see if we can get the same thing using calculus. So antiderivative, if we were to work backwards, okay, from that function, we would have the same negative x squared plus 3x. You don't need the plus c because you know the bounds, but I highly recommend drawing in that bracket and rewriting your bounds for -1. From here, it's just top minus bottom. It's plugging in numbers, evaluating, adding things together. So if we plug in 4, minus if we plug in -1, -16 plus 12 plus 1 plus 3. Looks like we get 0. You're doing okay? Do you guys think you can try the next one? Here, let's shade in the area together. We're going from -1 to 3. Okay. Don't worry about finding the area using triangles. You could do that, okay? But the antiderivative, aka calculus route, will work every time. If you want to do the triangles to check your work, that's fine. But I want you to definitely do the calculus. Do antiderivative. Any takers? If you do top minus bottom. Four. Does that sound right? Do we need to go over that? No? All right. If you guys are on a roll, try the next one. 0 to 5. Same equation, so we have the same antiderivative. We know the bounds, so we don't need the plus c, but you do need that bracket, 0 to 5. What did you guys get? -10? Sound right? Awesome. All right, what I want you guys to do is flip to page 346, a little bit backwards. We're going to revisit this one problem that you guys were doing the other day with all the midpoints, left rectangle, right rectangle. You guys remember this empty space in that chart? All right. So whenever you were going through this last section with all the different rectangles and trapezoids, you were approximating the area under the curve, and hopefully you noticed that as you let the rectangles or trapezoids get smaller, okay, the more accurate your answer was, right? We're going to try to find the exact area under the curve, okay? I think you put a star somewhere, what you thought was the closest one. we're going to now find the area exactly because we now know the fundamental theorem of calculus, okay, how to do it by hand using the antiderivative. So as a refresher, we were trying to calculate the area, I believe, from 1 to 7. So those are the bounds. And the function was negative 1/3 x squared plus 2x plus 5. Okay? Let's try to find the area exactly. So let's first think about our antiderivative. Negative 1/3 x squared. If you work backwards from that, what did you have before? If you add 1 to the power, that would be an x to the 3rd. But if you divide the coefficient by that new power, not quite. You need negative 1/3 divided by 3. Instead of dividing by something, you bring it up and multiply by the reciprocal. So this would be negative 1/9. You can always check your work. That's one thing with these antiderivatives. If you take the derivative, you should get this previous term. So if you did a derivative on this negative 1/9 x cubed, you should get negative 1/3 x squared. If you brought down the 3, okay, did that power rule, you can always check your work. That's what's nice about these. Let's work backwards from the next one. You have a 2x. What did you have before? Be an x squared. You have a 5. What did you have before? A 5x. Okay. If you wanted to check, okay, take the derivative of this, you should get what you had previously. You don't need the plus c because you know the bounds, but we're going to throw in that bracket. All right, so this is when you might need your calculator. We're going to do top minus bottom. Plug in a 7 for all those x's, see what you get. And then you plug in 1 for all those x's, see what you get. And then subtract your values. You should get 40. All right. Hopefully that was close to the starred one that you did. All right, we'll do some more of the antiderivatives tomorrow.